Okay, welcome to 3.1, exponential and logistic functions. So we have three objectives here. I will be able to identify an exponential function and identify it as growth or decay. I will be able to graph an exponential function using transformations, and I will be able to graph a logistic function. So what does an exponential function look like? So it'd be f of x equals a times b raised to the power of x. And this is where a is a non-zero, so that cannot be 0, b is positive, and b does not equal 1. Okay, does not equal 1. 1 raised to the power of anything would still be 1, and then 1 times our a would just give us a constant here. We would just have a number. Okay, so let's look at these. Consider the function f of x equals 4 to the power of x. Is this an exponential function? Okay, well, let's look at our rules here. It has to be in the form of a times b to the power of x. Well, our power is the variable, so that looks good. I don't see an a there, but remember that in a lot of cases, a is just going to be 1. So 1 times 4 to the power of x. Is a non-zero? Yes, it's a non-zero because it's 1. Is b positive? Well, 4 is positive. And does b not equal 1? Yes. So is this an exponential function? The answer is yes. Pen doesn't seem to be working today. Compute the following table and construct a graph. So we want to see what this looks like. So we're going to create a table. Okay, so that's always a way that we can graph something, is to create a table, but there are going to be shortcuts. So we want to be able to use those shortcuts as well. Okay, so if I put in -2, I have 4 to the power of -2. Remember, a negative exponent just puts the base in the denominator. So I have 4 squared. And 4 squared is 16. So this would be 1/16. This is frustrating. Okay, 4 to the power of -1. Well, just put it in the denominator, so we get 1/4. 4 to the power of 0. Well, anything to the power of 0 is just 1. Then 4 to the power of 1/2. So 4 to the power of 1/2. What is this telling us? Well, remember, this is going to be the square root of 4 to the power of 1. So the square root of 4 is just 2. Now 4 to the power of 1, it's going to give us 4, and then 4 squared is going to give us 16. Okay, so let's graph some points over here. At -2, we are at 1/16, so we're really, really close to the x-axis there. -1, we're at 1/4. 0, we're at 1. 2, let's see, 1/2, we're at 2, so 1/2, we're at 2. And then 1, we're at 4. 1, 2, 3, 4. So you can see this is growing. 1, 2, 3, 4. And 2, we're way up here. So it is never going to cross the x-axis. And then it's going to shoot up like this. Okay, and hopefully you remember this from our basic graphs when we looked at that. But we did see that whatever it's zeros, it's always going to cross at 1, because anything to the power of 0 is going to put it right there, as long as a is 1. So we'll look at that in a little bit. But this is our anchor point here. And then anything to the power of 1 is going to be the base. So 1/4 is going to be our base here. So is this one growth or decay? Well, it's getting, as the x's get bigger, the y's are getting bigger. So this is growth. And what is the factor? So what is this increasing by? Well, as we go up by 1 over here, we end up going up by times 4. So up by 1 times 4, up by 1 times 4. Here, up by 1's way, we're not going up by a half, but up times 1 be times 4, and so on. So our factor is 4, which also happens to be the base. So whatever b is going to be our factor. Okay, so now let's consider this function, and let's go ahead and fill in the table and see what happens. Compute the following table and construct the graph below. Feel free to pause the video and try to construct this table by yourself. Okay, so we're going to have 8 times 1 over 4, and it is just the 1/4 that is being raised to the power of x, and in this case it's -2. The negative is going to flip the fraction, so this becomes 8 times, flip this, we have 4 squared, which would be 16. Multiply this together, and we end up with 128. And this video is going to be twice as long because I can't get my pen to work. All right, so do that again with -1. The -1's just going to flip the 1/4 over, so we have 8 times 4 equals 32. Then we have 8. Well, anything to the power of 0 is 1, so this is going to be 8. And then we have 8 times 1/4 to the power of 1, so just 8 times a fourth is going to give us 2. And then lastly, 8 times a +2 is going to be times 1/16. Multiply those together, 8 times 1/16, and we get 1/2. So go ahead and plot these points and then see if you come up with the same graph as I do. Okay, there we go. You can see that instead of crossing at 1, it's crossing at 8. Well, why is that? That's because our a is 8. So when we plug in 0 for our exponent, we end up with 1. So our a is actually the intercept. Very cool. That happened up here too. We said that our a is 1. Well, there is our intercept. Okay, so down here, it's not going to cross the x-axis. This should probably be approaching a little bit better. I kind of went up trying to draw a straight line, but it's not going to touch the x-axis. There's a horizontal asymptote there. Are we showing growth or decay here? Well, as the x's get bigger, the y's are getting smaller. They never get to the negative, but they keep getting smaller and smaller and smaller and smaller, approaching 0. So this is going to be decay. And then what is the factor? Well, the factor is what it is going up by. And so if I take 1/28 and multiply by 1/4, 32 and divide it and multiply by 1/4, 8 times 1/4, well, that's just the base there. So you don't need to find the pattern in the table if you have your equation. Okay, so how do we know if it's going to be growth or decay? We already know the growth or decay factor is b, this right here. And then how do we know if it's going to be going up or down when you go left to right? Well, if the b is bigger than 0, so in the above example, then we have growth. As opposed to if the b, not if the b is negative, right? Because up here we say that b is positive. So it's not if the b is negative, but it's actually if the b is a fraction between 0 and 1. So you see we had a fraction here between 0 and 1. So this fraction caused this to be a decay function. So the b is greater than 0, but less than 1. Okay, so now we're going to talk about a special exponential function that we see a lot, and it's called the natural base, or it starts with the natural base, if I can get this written down, of, that should say of, an exponential function is e. N is approximately 2.718. All right, so the natural base of an exponential function is e, and this number e, it goes on forever just like pi, and so we round it off typically at 2.7 or 2.72 or 2.718. I'm going to put in all 3 decimals in this case. A lot of times we'll just use the e on our calculator. If you want to know more about where this comes from, feel free to look this up and read about it. I'm not going to get into that detail in this video. Okay, when the natural base is used in an exponential function, the function it is called the natural exponential function. That is horribly written. I'm having all kinds of pen problems, but make sure you write down the natural exponential function. Okay, so here's what that looks like. And notice that our b, it's the natural base, so our b just disappeared and we put an e, and that e is a constant. Okay, it's not changing, it's always going to be this number. Okay, so exponential growth. Well, if this e isn't changing, the growth isn't going to depend on it. In the previous examples, I showed you that the growth is when b is greater than 1. Well, e is not going to change. So what is going to change is, notice there's something new here, a k. So when k is greater than 0, we have exponential growth. And when k is less than 0, we have exponential decay. And then our growth or decay factor, well, that is the base, but remember that the base is e. So 2.7, and then however many decimal places you want. And actually, let's not make this equals. It's approximate to. All right, so now let's get into, we now know what these functions look like. Let's get into graphing them. Okay, so here's some basic functions. Now, typically we would have b here, but with b, if we have a b, we can't technically graph it. We could call some spot on here b, but I put in a 2 just so we have something to refer to. So what's our a here? Well, our a, if nothing there, is just 1. So you can either just remember that it's going to be 0 and whatever a is, or you can actually think about plugging in some numbers here. And that's what we did before when we were graphing these. So 0, 2 to the power of 0 is 1, and then to the power of 1 is 2. So now I know I'm at here, and 1, 2, just like this. And that's going to be enough for me to graph this because I know that there is a horizontal asymptote here at the x-axis. And this is a lot like the basic graphs that we were doing before. Okay, what about this one? Basically look the same. Okay, our a is still 1 because still, if I plug in 0, I'm going to get out a 1. So 1 right there. And then if I were to plug in a 1 here, this is going to be to 2.718. So we're just going to kind of eyeball it and say it's right about there. Okay. So really what I want here is some parent functions to work from so that way I can then apply transformations below and move that graph around. Okay, and so I'm going to quickly go over, I'm not even going to go over them, I'm just going to be applying those transformations. If you're forgetting all those transformations, look back in your notes, look back at that video about transformations. That was in video 1.6, it's still up, so you can take a look at it. Okay, so what's going to happen here? It says describe the transformation and then graph the function. So we know, and I set these up so that way all of these below here are a transformation on 2 to the power of x, and all these down here are a transformation of e to the power of x. So the natural exponential function. All right, so what's actually happening here? What is this minus 1 doing? Remember that if it's happening directly to the x, we're talking about a horizontal transformation, and in this case it's going to go the opposite. Remember, if it happens directly to the x, it does the opposite. So instead of going left, it's going to go right by 1. So those points, those anchor points that we found, are going to move over right. So we have 1 here, and we have 1 here, and it's still going to look like this with an asymptote right there. Okay, so what about now what's happening? Well, again, it's happening directly to the x, and this negative out front here is going to cause it to reflect. Now, where is it going to reflect? It's going to reflect horizontally, and I remember this was a challenge for some people to stick in their heads. But horizontal is this way, okay? So we're talking about a reflection that's going to occur like this, not like this. So let's make sure we get that on there correctly. Okay, so we were at 0, 1. Well, if I reflect that horizontally over the y-axis, it's actually going to stay in the same spot. And then it is this point that's going to move, just like that. Okay, I'm going to leave this last one for you. You're going to have to remember what a transformation occurs. If I'm multiplying by something out front, what transformation is occurring there? If I multiply the whole function, I'm not multiplying x, but I'm multiplying the whole function. I'll give you a hint that it is going to be something vertical, and now you have to think about what's happening there. Okay, coming over here. Now I'm multiplying something to the x, so we are talking about horizontal, and we're talking about doing the opposite of what we would expect. So a number greater than 1, you would expect it to stretch it, but when it's happening directly to the x, it's going to do the opposite, and it is going to shrink. Okay, horizontal shrink by 1/2 means that this point here isn't going to move because we're shrinking in relation to the y-axis, so we're getting closer to the y-axis. It's this point that was at 2.7 that's now going to be at 1/2 2.7. So we're kind of like that. So a horizontal shrink is going to make it a little bit steeper than it was before. Okay, and that's why I want you to be able to actually name them too, because sometimes it's kind of hard to tell from the picture. And I also want to know that you know what's happening there. Okay, so it's getting a little bit steeper. All right, what about this one? Well, if here it's reflecting over the y-axis, horizontal, then here it's also going to reflect over the y-axis. All right, last one here is for you again. If you're able to figure this one out, hopefully this one will be clearer. I want to show you is what a logistic function is. So a logistic function is kind of like an exponential function. However, an exponential function is unrestricted, whereas a logistic function is bounded. Now notice I didn't say unbounded because an exponential function is bounded. It's bounded below. Look at this, right? All of these were bounded below. But this one, the logistic function is bounded. It's bounded above and below. So what does this function look like? Okay, I have two functions here. Make sure you take the time to write these down correctly. One where the base is b and one where the base is e. And when I have a base of e, I have to get the k in there because that's going to tell me whether it is a growth or decay. So what is my limit to growth? Okay, so in this case, the logistic function isn't going to grow forever. And this is used a lot in the real world because in a lot of cases, things don't grow forever. Populations can only grow to a certain point. A plant can only grow a certain height. If you have a bunch of goldfish in an aquarium, they can only reproduce until they fill the aquarium. So most growth situations are actually restricted, and so that's why there is the logistic function. So the limit to growth is always going to be a horizontal asymptote, so a HASI, at C. Okay, so this number above here tells us how far we're going to grow to. And then how do we know in this case if it's growth or decay? And it's a little bit different than what we were looking at before. Different, I really mean the exact opposite. So in this case, it's going to be a growth function when we have a fraction between 0 and 1 for the b, or when k is negative. So what I've written here is actually a growth function. Both of these are growth functions because you can see the k is negative. Well, I guess we don't really know for this one. But for this one, it's definitely a growth function because the k is negative. So decay then would be that b is greater than 1 or k is greater than 0. All right, so let's take a look at graphing these. We're going to do these a little bit differently. There's going to be some steps here to it. So determine if it is growth or decay. Well, we just need to look. We have a base here. It is not e, so we don't even need to find, there shouldn't be a k there, which there is not. So we're just going to look at the base. Well, 0.3 is a fraction between 0 and 1. It's a decimal between 0 and 1. So this is going to be growth. And this is what we're predominantly going to be working with is growth logistic functions. All right, so find the horizontal asymptote. There is always one at C and one at the x-axis, which is the line y equals 0, right? So x-axis or y equals 0. Okay, so let's go ahead and draw that in. We're doing an asymptote there with a dotted line. And now I need to find the y-intercept by substituting in x equals 0. Because remember, I know the y-intercept is when x equals 0, and I just need to find out what y is then. So f equals 0 equals 10 over 1 plus, I'm having to pause the recording so I can take my time writing this since I'm kind of struggling here. All right, so here we go. This is going to just be 1. 1 times 4 is just 4. 4 plus 1 is 5. 10 divided by 5 is 2. So this all simplifies out to 2. And notice in this case it wasn't the a, right? So you're going to have to be careful of that. Don't just assume it's going to be the a when it's a logistic function. So our intercept is at 2, and then the logistic function, if you remember back from our basic graphs, it looks like this, where it's approaching, shouldn't be going up, it should just be getting closer and closer to the x-axis. Okay, there you go. All right, so follow those steps and give these a try.